The IID sample mean is expected to be the population mean, no matter what the sample size. The SD of the sample mean gets smaller as the sample size increases, and so this leads to a very natural conclusion, which is that if you have a large sample, then your sample mean is very likely to be close to the population mean. And now here are a couple of English words that need to be made precise. We've got large, we've got likely, we've got close. So there's a result called the weak law of large numbers, which makes all this precise. Yes, there is a strong law, but we won't be dealing with that in the class. A special case of the weak law is the law of averages that you've known since Data 8. But we'll come to that once we have stated and derived the weak law. Now we're going to show that the random variable xn has high probability, likely, of being close to mu, and when mathematicians want to talk about close, they give themselves a little interval around the point that they want to be close to, and to do that you might want to consider a very small width epsilon. So I've just said let epsilon greater than 0, so it could be enormous, but it's a good idea to imagine it to be quite small. And what we're going to look at is the probability that our sample mean differs from the population mean by more than this tiny amount. And I'll make a little note somewhere in perhaps a different color that what we're doing here is the probability that the two random variables are not close. Because we're saying look at the chance that the distance between the two is bigger than some number, right? We are going to show that this probability goes to 0 as n tends to infinity. As the sample size gets large, this probability goes to 0. So the chance of being not close gets small, so the chance of being close gets large. And this is true for every single epsilon. This statement is the weak law of large numbers. Now, showing it is actually rather straightforward. Because look, this is a random variable. The sample mean, and what's mu? Mu is its expectation. So we have random variable minus its expectation. That distance has to be greater than a certain quantity. This is sounding very Chebyshev-y. So in fact, let's just try applying Chebyshev. The chance that the sample mean exceeds its expectation by more than epsilon is at most the variance of the sample mean divided by the square of that threshold. divided by epsilon squared. Now, what's the variance of the sample mean? Well, the SD of the sample mean is here, and so that's equal to the square of sigma divided by root n. That's the variance. So you have sigma squared divided by n epsilon squared. Now sigma is constant, epsilon is constant. It's n that is increasing, and so as n increases, this goes to 0. Done. And so if the chance that x bar n, the sample mean, is far from mu is going to 0, then what about the chance that it's close to mu? That is going to 1. Another way of writing this is the chance that your sample mean is in the interval mu plus or minus epsilon. That goes to 1 as the sample size gets large. So if you want to remember the weak law, this is a very, very good way to remember it, because it's picking up the heart of the matter. You have your population mean mu, and you've given yourself a tiny little interval around it. And what the result is saying is that the chance that your sample mean is in that tiny little interval is extremely high if your sample size is large.